Alrighty. Okay, so we're going to talk some more about surfaces in space. If you're given an equation, what does it look like? Is the broad stroke. What does the set of solutions to that equation look like? Okay, so we know how to do stuff like this. A couple different points of view you can take on this equation here. For one thing, it's got a bunch of rotational symmetries, right? It's rotationally symmetric around the z-axis. It's rotationally symmetric around the x-axis, etc. Okay. Also, you can observe that this is saying that the distance to the origin must be 13. Right, so that's really easy to interpret this as a sphere. Okay, all right, but here's a different equation. And what I want to talk about is how would you figure out what this thing looks like. This does still have a rotational symmetry, and that's nice, right? But let's temporarily set that aside. This equation is not the same. But it's got something in common with the original equation we were looking at. So specifically, you can get this equation by, in the original equation, everywhere you see a z, replace it with 2z. Right? And then that turns the first equation into the second equation. Now, of course, you change the equation. No surprise, that's going to change the solutions. Of course it is. What I want to talk about, though, is if you do this process, everywhere in the equation, if you replace every single z with 2z, is there like a pattern can you interpret geometrically what that does to the solutions? And it turns out it totally does. There's a very simple geometric interpretation. So the way I like to come at this is by considering for example, that point. This point here is on the sphere. That's a geometric statement. The algebraic version of that is if you take these coordinates and plug it in, the equation works. Right? So we have a point on the sphere. Now, what would happen if I took this point and let's take those coordinates and plug them into there? Will that still work? And no, of course not. You changed the equation. You messed it all up. Right? So that's not going to work. But we can see how to fix it. The idea is that the reason this doesn't work anymore is because this z-coordinate of 12 that went in there and got squared is getting messed up. It's going to get multiplied by that 2 first before it gets squared. And that's why it doesn't work anymore. I'm just loosely speaking, right? Okay. All right. So the clever idea then is to fix it as follows. Let's take that point, throw it away. Let's consider instead this point, where I divide the z-coordinate by 2, right? And now, having anticipated this multiplication by 2, this 6, plug it into there, gets multiplied by 2, becomes the 12 that gets squared, and all the rest of the arithmetic works just like it was supposed to, and the equation works. Okay, so here's another way to say that. If algebraically you do something like this, right? You replace every z with 2z. Then you can kind of balance that off by taking all the z coordinates and cutting them in half. And that dividing them by 2 balances with the anticipated multiplication by 2. All right, now let me say that a little bit differently. Dividing the z coordinates by 2 is effectively the same as taking this point and pulling it toward the xy plane. Halfway, right? Halfway to the plane. And let me say that a little bit differently. The solution set itself, it's like we're taking this solution set and we're squishing it. Right? Every point on it is having its z-coordinate cut in half. It's like it's getting squished toward the xy plane by a factor of 2. So that's the nice punchline, and the way I like to say this is that when you do something algebraic to an equation, what happens to the solution set sort of opposes that. So whatever you do to the variables in an equation, sort of the opposite happens to the solution set. And you'll see this pattern in lots of different examples. So here's a bit of a weird one, honestly. That equation we've already studied. We know that's what that looks like. Right? What would happen if in this equation everywhere I see a z, what if I were to replace that with a negative z? Okay, well, multiplication by -1. What's the? How do you undo a multiplication by -1? Well, you multiply by -1, right? That is its own sort of undoing. So what happens then? This new equation, where z has been replaced with -z from the previous equation, all the z coordinates just go negative. So everything effectively then just flips, is reflected, maybe better, through the xy plane. Okay. Bunch more examples. Same idea, different context. Let's look at this ellipsoid. Well, this is not, algebraically, it's not terribly unlike this equation that we were just looking at a minute ago. That, I know, is the equation of a sphere. And I can tell you how to algebraically, what kind of manipulations do you have to do to this top equation to turn it into this new equation? Well, you've got to replace x with x over a. Now be careful. You're going to want to say, hey, aren't you dividing by a squared? Well, you're dividing x squared by a squared, but what are you doing to x itself? Keep in mind that this little term right there, that is x over a squared, right? So we're really replacing x with x over a. Everybody see that? Okay. All right. So in order to turn this into that, I am replacing x with x over a. Okay, so I'm going to be, what's the opposite of dividing by a? Well, it's multiplying by a. All the x coordinates are going to get stretched out by a factor of a. So this thing is going to get, stretched outward away from the YZ plane by a factor of a due to that. And then analogously, it's going to get stretched in the y direction by a factor of b. It's going to get stretched in the z direction by a factor of c. And so, and now let me zoom in for so I can draw on here. It's like we had a little sphere of radius 1. Right, and it got stretched by a factor of a in the x direction, by a factor of b in the y direction, by a factor of c in the z direction. And thus we get, now you just think geometrically, what happens when you take a ball and stretch it in various different directions like this? Well, you get something like this, and this is called an ellipsoid, because the cross sections are all ellipses. Alrighty, so now do notice this equation that we were just looking at here. You can't attack that equation directly with a rotation argument. Right? And I guess you could with a cross-sections argument. But again, cross-sections arguments are, they're geometrically very challenging in terms of, okay, I've got all these different cross-sections and I need to kind of assemble them together and make everything fit, all while thinking three-dimensionally but drawing two-dimensionally. Yeah, it's hard to do, right? And again, sometimes that's all you have, sometimes you have to. But I think this is a much more conceptually natural way to answer a question like this. Okay. All right. Let's look at this next one here. This is called an elliptic paraboloid. We'll talk about the name in just a moment. But this equation, where does that come from? Well, that's what you get when you take this equation, x squared plus y squared equals z, whose solution set we know right? And you do, again, certain very clear manipulations. Everywhere you see an x, you replace that with x over a. Thus, I stretch by a factor of a in the x direction. Everywhere you see a y, you replace with y over b. And everywhere you see a z, you replace with z over c. So it's stretched by a in the x direction, b in the y direction, c in the z direction. And so, for example, a point like this one, let's take that point there. That's 1, 0, 1. That's easily seen to be on that surface satisfies that equation, right? That point, when you stretch it by, as described, turns into that point there with coordinates A and C, like that. How we doing? Is everybody on board? Okay. All right. Okay. I don't know why I'm erasing that. Let's just leave that there. It's not hurting anybody. Okay. I'm going to let y'all read this last example for yourselves. Start with a more familiar cylinder. Make a stretching argument. Persuade yourself that the result looks like this. That's an elliptical cylinder. Okay. All righty. Okay. Do be careful with applying these kind of deformation arguments. The order matters. You got to be careful. I'm going to take you through this first one, this one example of where there's two sort of deformations in succession that relate to each other, where the order really does matter. Let's start with. Okay, so the question is, what does this thing look like? And again, it's not exactly a sphere, but it's not hard to see that structurally has a lot in common with that equation, whose solution set we do know that is a sphere, unit sphere, easy starting point. And let's ask, what do we have to do? How do we manipulate this equation to get to the equation we're interested in? Well, the first thing I'm going to do is I'm going to replace everywhere I see an x, I'm going to replace with x over 3. And you can see my motivation, right? I got that little business right there. Now we've made a little progress. This looks a little bit more like that. Having done this thing, replace x with x over 3, that stretches in the x direction by a factor of 3. So what had been a sphere, unit sphere, now it's kind of stretched out, and so it's an ellipsoid, and not hard to argue that this point 1 on the x-axis gets stretched out to that point 3, and that point -1 gets stretched out to -3. Is everybody on board? Okay. All right, now here's where students make a very routine mistake, and it's an easy mistake to make, but it's important. How do we deal with the -1? We need to get a -1 in there, and a lot of students think to themselves, well, but don't I have to, I want to do the -1 thing, but this is kind of what x, it's certainly what x was, so shouldn't I subtract 1 from that or something, right? And what you have here is trying too hard, right? It's overthinking. It's much simpler than this, right? The way you proceed from here, okay, is to observe that this equation and that solution set have served their purpose. We no longer need them. We're certainly not obligated to them, and let's just forget about it. Right? It's gone. All right. So let's ask a much simpler question then. What do you have to do? What would you replace x with? X. Not some distant nostalgic memory of where you feel like x used to be. Right? But x, there it is. That's x. And what do you replace this x with to turn this equation into that equation? And that's real easy. Replace x with x minus 1. Don't worry about the -3. It's not hurting anybody. We're replacing x with x minus 1. Everybody on board? And replacing x with x minus 1, we get a translation. Right? Here you go. X replaced with x minus 1, and everything shifts over by 1. So that what had been a 3 vertex is now a 4, and what had been a -3 is now a -2. Yep.
Is there any order to how do you do the stretch first or the translation?
Yeah, you're actually free to do it in either order. You just have to, when you do it, you have to do it correctly. That's the rule. So now here is a combination that got us to where we wanted to be, and I'll make some comments in a moment on it. Sort of, if you wanted to do it in the other order in some sense, you do have to change some things around. But there's no sort of magic right. It's not like you have to do stretches before translations. I tend to like to do stretches before translations. I think it works out a little prettier. But it's free country. Great question. Thank you. Okay, is everybody on board with what happened here? Okay, so, all right. So this that was the equation we're interested in, and here's what it is. It's an ellipsoid centered at 1 on the x-axis, and with blah blah blah. Okay. All right. So now to your question. Here's an alternate thing that you could have done, and this would have been perfectly fine, but harder. I think harder. Algebraically, notice that that's equal to that. Nothing happened. Right? But you can view this then as the succession of edits in sort of the other order. If you replace x with x minus a third, have that be your first step, so a translation by 1/3 in the x direction. And then after that, replace x with x over 3. Now again, that minus third just sits there. That minus third is not part of x. You don't somehow divide it again or something like that. It's just sitting there. Replace x and only x with x over 3. And so when you can see what we have here is we have a translation followed by a stretch, and that does get us to the same sort of algebraic endpoint. Right? So that's fine. And you can totally do it that way. Let me point out something ugly about this, though. If you do this, well, first of all, you got to deal with fractions, right? And so, that's already kind of a downer. It's just a little bit more inconvenient. It's a little bit harder to draw on the picture. It's suboptimal. But here's another downer. When you do this second step, when you replace x with x over 3, you've got an already translated, actually I'll just do it down here. You've got an already translated thing. So your sphere is now off center, centered at 1/3. And let's think about what the stretch does to this. A very common mistake students make is feel like, well, when you stretch something, you stretch it from its middle. Right? Doesn't that just feel right? But you don't. Keep in mind, why do we interpret this as a stretch? We interpret that as a stretch because the x coordinates are getting multiplied by 3. And if you say it that way, the x coordinates are getting multiplied by 3, you start to realize the x coordinates of points on this surface are thoroughly unaware of where the center is. Right? If the x coordinates are getting multiplied by 3, that center is not going to stay where it is. So, said differently, we're not pulling this thing from its middle. This thing, we're pulling it from the YZ plane. So, the points over here are going to get stretched further because they're further away from the YZ plane. And the points over here are going to get stretched less because they're closer to the YZ plane. And so not only does the thing get longer, but the stretching of it moves the center of it. And how far does it move the center? Oh, well, that gets weird and confusing, right? So I think it's much harder to make the argument in this direction. I strongly encourage not doing this. Free country, you can do it if you want, right? But again, the rule is you have to do it correctly, right? And it's going to be harder to do it correctly if you do it the hard way. Does everybody see what I'm talking about? Okay, so moving along. So we are now into chapter 13. We're still not quite going to do any calculus today, but we're getting close. We're going to start doing calculus on Wednesday. Okay. All right, so I have to tell you what a multivariable function is. And a lot of y'all may have memories of learning what a function is a long time ago. And the way it's often described in a high school setting or a single variable calculus setting is that a function takes a number in and gives you a number out. Has everybody heard that one? Perhaps? Okay. All right. That is a certain kind of a function. That's what's sometimes referred to as a single variable function. single variable real valued function. And that's fine and everything, but there are many more functions than just that. Really, in general, a function, I'm going to speak a little sloppily here, forgive me, is a function where anything could go in and anything could come out. There's no rule that says it has to be one number in and one number out. It could be a bunch of numbers in, a bunch of numbers out. It could be, an animal in, a color out. There's no rules. It could be anything. All right? Now, we're not going to go that far in Math 212. But we are going to talk about multivariable functions, and in a multivariable function, several numbers go in. Very importantly, not just one number. A bunch of numbers go in, and then quite possibly a bunch of numbers might come out. That's still a function, but you can see now why we call it a multivariable function. Okay. All right. Now, observation, an ordered list of numbers, that is the input. Well, an ordered list of numbers, I could think of those as the coordinates of a vector in Rn. So instead of thinking of this as a bunch of numbers going in, we can make a vector approach, a vector interpretation, and likewise with the outputs, these outputs, I can view those as being coordinates of a vector coming out. I can think of a multivariable function as one that takes a vector in and gives you a vector out. Another common way to say it, way to think about it, and arguably a better way to think about it, really. There's certain big advantages to thinking of the inputs and outputs not as a bunch of numbers, but as single vectors. Okay. All right. Alrighty. Let's see an example in a minute. There's a little bit more notation first. Sometimes this gets represented like that. The idea is that we've got this Rn over here where there's a bunch of input vectors, which when you go through the function, that little arrow is supposed to be representing the process of those going through this function f, and then out comes another vector. So this notation, very common, see it all the time. Here's another one. This more common, perhaps. This notation says, all right, this function is called f. The colon here says, okay, I'm going to tell you some stuff about this function now. This function has as its domain, namely the world where input vectors come from, is Rn, and the target, namely the world that output vectors land in, is Rm. Right? So this is telling you what the name of the function is, what kind of inputs it takes, and what kind of outputs it creates. So, again, it's just notation. Okay, so here's an example. There is a multivariable function. It's got three inputs. Right? It's not a single number going in here. We've got x, y, and z all going into this function at the same time. You might say a vector in R3 is the input. Right? And then what comes out? Well, what comes out is a couple of numbers, two numbers in that order. Oh, well, you can think of that as a vector in R2. So we can refer to this function here as a function from R3 to R2, and we'll use that terminology a lot. So again, be ready for that. You might want to give these things names. This input vector that lives in R3, be convenient perhaps to call it just X vector, right? And this output. Now here's the formulas for the output. The formulas tell you how to compute them. They aren't particularly convenient little labels. Right? So it'd be nice to give these outputs names. I'm going to say V1 is the name I'm going to give to that output component, and V2 is the name I'm going to give to that output component, and then altogether I can say the output I will label as just V. Okay. How we doing? Is everybody on board? Just pretty much notation, just kind of stretching, kind of generalizing the idea of a function from a single variable context to a multivariable context. So why is this worth anything? What does this have to do with the real world? Is this just mathematicians making up hard problems so they can solve them. No, so the world is chock full of multivariable functions. And just a couple of quick, easy examples. The book's got a bunch in there as well. Just the weather, right? I mean, polite elevator conversation, right? Can be thought of as a multivariable function, right? So the idea is that depending on where you are and when you're talking about, at any given place and time, you can talk about, well, what is the weather at that point? So what's the temperature there? What's the barometric pressure? What's the humidity? Right? So there you go, a multivariable function. You give me 3 inputs. That describes a place and time at which the outputs are the corresponding weather. Everybody happy? Okay. All right, here's another one. Econ majors in the crowd. Not at all implausible to think of how risk, right, if you have some financial situation, how much risk do you face might be viewed as depending on, how much capital have you invested and how much labor have you hired and what's the prevailing interest rates these days and et cetera. So ditto profit. Your expected profit will depend on these same things. And so you can view this as a multivariable function that with these inputs you can speculate about these outputs. So you have a function from R3 to R2. Everybody on board? And let me just remind you, this is another great situation in which to talk about, the reason that we shouldn't confine ourselves to 3 space. Again, the first reaction that people have when they're thinking about multivariable calculus is, okay, well, for one thing, we'll never leave 3 space. We live in 3 space, and it's all science fiction to talk about the 4th dimension, right? And so what a ridiculous thing to entertain. But no. You could easily imagine that these things here, risk and profit, might depend on, in addition to these, maybe also tax rates. Or something. And now, check it out, our domain is 4-dimensional. All right, there's nothing science fiction-y about that at all. Not even remotely. Okay. All right. All righty. Okay, so multivariable functions. We're going to talk now about how to draw multivariable functions. And good news, bad news. There's multiple different ways to draw multivariable functions. So it's good news in the sense that, well, yeah, these are complicated objects, and it's good to have options, different ways that we might be able to view them, and that's nice. That's a good thing. Right? Here's the bad news side of the fact that there are multiple ways to represent multivariable functions, and that is you have to be clear in your mind of which one are you using. Right, so we're going to talk about something called graphs in just a moment, and we're going to talk about something called level sets shortly thereafter, and eventually, well, in fact, come to think of it, we already have talked about parameterizations, right? And it turns out, if you think about it, in all of these cases, given a function, there's a corresponding picture, right? If somebody gives you a parameterization, you can see what that traces out. Picture, right? So, all of these things, and there are more than just these 3, are connections between algebra and geometry. Very valuable, very important. But they're all different. Right? So if you have a function and draw a level set of that function, you have to know that you are drawing a level set and not a graph. Because understanding that you have of graphs, if applied to something that is not a graph, results in garbage. Let me say that a little bit differently. We're going to talk about the calculus, loosely speaking, the calculus of graphs. We are also going to talk about the calculus of level sets. And we're going to talk about the calculus of parameterizations. They're all different. Right? So if you apply an idea of calculus of graphs, but you apply it to something that's a parameterization, then you're not making any sense. Right? And you're going to get dramatically wrong answers, importantly wrong answers, and not sort of, sympathetic, happens to the best of us. It's importantly wrong. Your bridge will fall down. Right? So it's in order to make sure that these bad things don't happen and you don't inadvertently say garbage, you have to be very, very careful here going forward watch your language. It's so easy to mess this up. We've all been trained since, I don't know, what is it, middle school? That when you draw a function, you draw the function, and when you draw a function, that's the graph or something. It's just that's what the function is, and what's the difference? It's going to really matter going forward. By the way, here's why it's always kind of worked out for y'all in the past, and that is that almost every picture that you've ever drawn of a function in the past has been a graph. Practically all of them. Right? And so there hasn't really been so much opportunity for confusion in the single variable context. In this multivariable context, we're going to be drawing a lot of pictures that are not graphs. And so lots of opportunities for problems. Okay, so all right, there's that speech. All right, what's a graph? A graph says you take your function and you set it equal to a new variable. Let's call it y in this case. So we have a function with input variables x. Take the output, call it y. The graph is what you get when you take all of these input variables. From there, you take the output variable there. The graph is the collection of all of these points formed by sort of concatenating those coordinates like this. So here's an example that I think might be relatable. Let's consider, here we have a function from R2 to R1, 2 inputs, right? 1 output. Function from R2 to R1. Now, if I give you an x, let me use my colors more consistently. If I give you an x1 and an x2, right? You can take that x1 and x2 and plug it into the function. That gives you f, which then also gives you y, that being your y coordinate. And you can take these and put them together, the x coordinates that were inputs, the y coordinate that was the output, and this point, right, that has those coordinates, that point is part of the graph then of the function. Okay. The graph then would be a surface. Yeah.
Is there any significance to being x1 and x2, or could x2 also be thought of as like z?
Yeah. You could. I mean, the names you put on these variables could be different in every context. It's sort of the user's choice. So I'm using x1 and x2 just to make them cosmetically look like each other. But yeah, you very naturally might have x and y as inputs and z as the output. Or depending on what your kind of application you're doing, you might have P and Q as your inputs and R and S as your outputs, or something like that. Yeah, totally. Right. Okay, so I claim you're generically going to get a surface here, and the idea is that for any inputs, there is a corresponding output telling you how much to go up. Well, the inputs came out of this plane, if you will, loosely speaking. So for every point in this plane, you're going to, by way of this function, be instructed to push up by a certain amount. And when you take this plane and kind of push different points up by different amounts, I appeal to your intuition, you would expect to get a surface. Okay. All right. Let's take a quick moment to recall how this is familiar from the old idea of graphs, right? If you have a function from R1 to R1, where x, let's say, is the input variable, well, I could give a name to the output variable and say, let's let y equal to f of x. Now I'm choosing this new y to be the name of the output variable. When I write down that equation, y equals f of x. Now I have an equation, and you end up drawing a picture, something like that results from this equation. And let's think about the numbers. The x input, for any given x input from the x-axis, f gives you the y that tells you what the output value is, and therefore how much to push up, thus resulting in the graph being a curve. Yeah? Okay. All right, so this is just a generalization of that same idea, just that now you have two input variables instead of one. You get a two-dimensional graph surface instead of a one-dimensional graph curve. Okay. All right, so that's one construction. Let's talk about level sets. This is a different construction. Importantly different construction. You got to be really, really careful with this. Again, we've all been trained very, very badly with lingo to use the word graph kind of synonymously with the word picture, and you really got to be careful. So please, and I know everybody's kind of encountering this problem, this the need to resist this reflex kind of for the first time. I know it's going to be hard. You're all going to mess up. I mess up from time to time myself still, but do please, make the effort to try to resist that temptation now. Okay, so here we go. Let's suppose you have a function like this. So it's got n-dimensional inputs, one-dimensional output. A level set is the set of solutions to an equation like this. And a lot of students will look at this and say, that doesn't look all that different, right? F of x equals c as opposed to f of x equals y. The important difference is that y was a new variable, and this, very importantly, is not. Here, we're setting f equal to a constant. That's what a level set is. A level set is what results from setting f equal to a constant. Everybody on board? So here's an example. Let's look at... here's a function from R2 to R1. By the way, we just got through drawing a graph of a function like this with two input variables and one output variable. We ended up with a surface, right? So now the sloppy temptation is to say, a function from R2 to R1 is a surface. You're gonna, again, that's the reflex, but no, the function from R2 to R1 is not even a geometric object. The function is an algebraic object. If you want to talk about a geometric object, you've got to be very crisply clear which kind of construction are you using. What we did back here is we formed the graph of that function. The graph was a surface. Yeah. Not the function itself. So, what happens now, this kind of a function. We're not going to make the graph. We're going to do a different thing. We're going to take the level sets. Level sets are what you get when you take your function and set it equal to a constant. So I'm going to say here equals c. This equation, where I set h equal to c. Now let's think about what we have there. I've got an equation involving two variables, and that's going to give me some sort of a curve in the plane. All right, this is the H1, H2 plane. Oh, I'm sorry. I misread my own handwriting. L1, L2. Sorry about that. I'm going to pay better attention to my own writing. L1, L2. This is the L1, L2 plane. All right. Now, what constant do you pick? Any/all, right? So there are many level sets. You could draw as many as you have time and energy and patience for, right? So that is one level set. If you pick a different constant, if you say, okay, now let's look at C2, well, then you're going to get a different, you have here a different equation, certainly. This is no longer the same equation. We put a different constant in there, and that's going to give us a different curve. All right, so when we use level sets to represent a function, very often we will draw several level sets, not just one. Yep.
Will it always be a closed shape like that?
Nope. That's just a for example. Yeah, no, there's no such rule. Yeah. Right. Now, why did I draw this particular shape? A context that y'all might have conceivably seen is contour lines on a topographic map. Have y'all ever seen that kind of thing? You go hiking or whatever. They actually have them on Google Maps now. That's probably been a long time. But if you zoom at just the right level and you have the right options selected, I think you have to press an option that says like show contours or something like that. And if it's zoomed just right, they will show, like I can see the altitude line that says 600 feet elevation that goes almost exactly through my house. And then you can see the 620 and the 640, etc. So anyway, contour map, and this is a very familiar, very easy, natural concept that y'all mostly experienced, and they are in fact level sets. The altitude function being set to different values. You set it equal to 600, and you get a picture like this, and there's my house. Something like that, right? And then you set it equal to different value. Set it equal to 620, and then there's that other contour line, etc. Yeah. The weather gets reported in the form of level sets very often. A real quick picture. Did I draw a picture of this already? No, I didn't. Okay, let me do this real quick. Give myself a little space. Okay, so we're going to draw a map of the U.S. here. That kind of close enough. And y'all have seen the weather reported, and they'll do stuff like, let's see, it's really cold up there, and it's less cold in that range, and then a little warmer, maybe something like that, and then a little warmer still there, and then it's really hot down there. So we've all seen these kinds of pictures, right? So what we're actually looking at is kind of level sets. And in particular, they'll draw stuff like, let's see here, 40s, 50s, 60s, 70s, 80s. Right? And what they're saying then is they're saying that this line right there, that blue curve, that's where t equals 50. And this line right here, that's where t equals 60. Right? I mean, the barrier between the 50s and the 60s is 60. Right? Etc. So they're coloring in for visual convenience after the fact, but really they're reporting this function of two independent variables, the temperature function, two inputs, longitude, latitude, one output, degrees Celsius, right? Fahrenheit, whatever. This function from R2 to R1, and they're communicating it by way of level sets. Everybody on board? Yes?
So for the level set, do we never include the output axis then? Because this is
correct, because there's no output variable in the equation, right? If you look at the equation is just f of input comma input equals constant. There is no output variable, therefore there's no axis to include. Yeah, absolutely, right. Okay, why would they do this? Why would they, use a concept from multivariable calculus, right, to communicate something as trivial as the weather? I point out this is actually a really hard problem, how to communicate what the weather looks like across, a large area of land with a picture. Because what's your other option? You could try to draw the graph. That'd be a nightmare. Right? Can you imagine the weather person standing there holding the graph would be a surface, right? And he'd be like, okay, here's our graph model of temperature today, and look at this. See that high spot? Okay, there's this spot here, and the camera can't tell, but I can tell that that's sitting right above the Dallas, Texas, and then this lump here is going to start moving that way. This whole lump is going to kind of go over that. Like, it's just be a nightmare of inconvenience trying to communicate with a three-dimensional surface. Right? Everybody see the problem? Right? This is actually easier in that context. So level sets are a wonderful tool, very convenient, very sensible way to describe functions in different situations. Okay. Alrighty. Okay, now there is a relationship between graphs and level sets. I cannot emphasize enough. They are different things. Of course, they're different things, right? We just got through talking about, in this case, the graph is a surface in space. Level sets are curves in the plane. They're completely different kinds of things, right? That said, there is a connection between them, and I want to talk about that for a quick moment. Let's see here. Okay, we're good. Here's how you form the graph. Graph is what you get by setting the function equal to a variable, a new variable. A level set is what you get by setting the function equal to not a variable, but a constant, several different constants, right? Okay. So here's the thing. If you've set equal to a variable and would like to know how does that relate to setting it equal to a constant, clever observation, if you take that graph and then set that z equal to a constant, then out comes exactly that equation. Said differently then, a cross-section of a graph gives you an equation for a level set. Right, so a little bit of an oversimplification would be to say that cross-sections of graphs are level sets. And there's a little asterisk I have to worry about. But anyway, let's see an example. Here's a function that we've seen a lot of. Let's look at this function here. It's a function from R2 to R1. 2 input variables. Right? 1 output variable. I mean, there's a formula there. There's 2 different terms, but that is one formula, and therefore there is 1 output variable. Is everybody on board? Okay. Okay. Well, we can draw some level sets. If you want to do level sets are what you get when you set this equal to a constant. Right? You look at this equation where you set x squared plus y squared equal to constants. You get various circles. Flashbacks to algebra 2. That's what level sets look like. Yeah. Everybody good? On the other hand, what is the graph? The graph is what you get when you set that same exact function, not equal to constants, but equal to a new variable. Now we have 3 variables in this equation. This is a chapter 12 problem. What is this? What surface is the set of solutions to this equation of 3 variables? Now, conveniently, we've already studied this equation. We know what the answer is. It's a paraboloid. It's a bowl like this. Okay. All right. So now we can see the connection, though, between the graphs and the level sets. And the assertion was that cross sections of graphs give you level sets, and you can see it right here. If you take cross sections, let me do this with a pencil. Take a cross section there of that paraboloid, right? Horizontal cross, setting z equal to a constant. Right? No surprise, what you get is a circle, namely one of the level sets. Everybody on board? Now let me confess, there was a little asterisk that I put in while I was describing this. Technically, the cross-section of the paraboloid is a circle that lives inside of R3 and is, propped up at an altitude of C. Right, so, yes, it is a circle, but it's not exactly, technically the level set lives in R2, technically the cross-section lives in R3, okay, sure, you gotta be, aware of that distinction. I didn't mean to delete that. But with that, formality in mind, cross-sections of graphs are level sets. Horizontal cross-sections of graphs are level sets. How are we doing? Is everybody happy? Okay, alright. Okay, so the next couple of examples I have here are designed they're exercises in language. And again, you got to be really, really careful with the language here. By the way, I've made several old test questions. They were new at the time, but I've made several test questions that look a lot like this. The challenge in these questions is not the tedium of the algebra. Right? The algebra on these questions is really straightforward. There's nothing to it, right? So that's not what was being tested in these questions. What was being tested in these questions, and hey, I've done it before, I'll do it again, right? I have no promises to win, but you got to definitely be on the lookout for this kind of thing. What's being tested in these kinds of questions is, can you make a proper use of the language? Can you interpret the language correctly, and can you use the language correctly? Right. So anyway, here's the question. We've got this. I got a plane with that equation, right? And I ask very simply, what functions does this relate to? And I'll phrase this maybe a little more sort of instruction oriented on the exam. But let's just play along. What functions does this plane relate to? Is this plane the graph of some function? Is this plane a level set of some function? And what? Now, the big mistake that a lot of students make is to say, oh yeah, it's the graph of that function. That's just wrong. It is absolutely not the graph of this function. This function here, right, 2x minus y plus 3z, that has 3 input variables. The graph of a function of 3 input variables, when you add in the 1 output variable, has 4 variables. The graph of this thing that I'm calling g doesn't even live in space that we can draw. So if you say p is the graph of that function, that's really severely, catastrophically wrong. Everybody see what I'm talking about? And the calculus is going to reflect that. Right? Okay. So what does this function have to do with anything there? I mean, I can see it right there. Surely this has got to be important. Well, here's what it is. Equals a constant. That plane is a level set of that function g. Everybody on board? Okay. All right. So but this plane, is it a graph of something? What was it? Would it be the graph of? It's the graph of whatever it is, yet to be determined, perhaps, but whatever thing it is that you set equal to z. Remember, that's what a graph is. Graph means you have some function that you're setting equal to a new variable. And I ask, this is just an algebra question then, what is it that you would set equal to z to make something that's equivalent to this equation? Well, solve for z. Right? If you take that z right there and solve for it, you get an equivalent equation that's perfectly legal in reversible algebra. And having rewritten the equation like this, you see we are looking at a graph of that function. And that function, very importantly, notice 2 variables. So this plane in 3 space is a graph, but it's a graph of a function of only 2 input variables. Okay. There's another example related. Oh, I'm out of time. Another example down here, very similar. I'm going to let you all read your way through this one. Analogous, just pay note to the parameterization down here as well. And see y'all later. Have a good Monday.